Hello ladies and gentlemen, thank you for joining. My name is Alexander Dijkshoorn and I'm a PhD student at the Robotics and Mechatronics group at the University of Twente. Today I would like to tell you about the work of my co-workers and me on 3D printing of soft cantilever flow sensors, called First Results of a Soft 3D Printed Resistive Cantilever Flow Sensor. First, I will give you a short introduction of the arguments for the study and the sensing principle. Then I will elaborate on the methodology and results. I will end off with a discussion and conclusion. Cantilever-shaped mechanosensors can be found a lot in nature, where they can have purposes like flow sensing and tactile sensing. The different geometries and material properties from these cantilevers allow for this wide range of functions. They are also a source of inspiration in terms of improved sensitivity, noise levels, and frequency response. The operation of, for example, micro-aerial vehicles could benefit from bio-inspired flow sensing, since distributed flow sensing is probably essential for complex flight performances. Multi-material 3D printing with fused deposition modeling is a technique that holds potential for the fabrication of embedded sensors. This has advantages like reduced cost and assembly time, while also reducing packaging constraints. Therefore, in this research, we want to investigate the possibility to 3D print cantilever sensors for flow sensing. Several examples of 3D printed flow sensors and cantilever-based sensors can already be found in literature, where most 3D printed flow sensors use a resistive transducer. An example by Al-Rubaii et al. Is shown on the top right, showing a clamped beam configuration with a strain gauge. Fully 3D printed whisker sensors or cantilever sensors also exist. However, as far as we know, they have not yet been used for flow sensing purposes. One example of a soft cantilever flow sensor is that of Kamat et al., where they use 3D printed molds for fabrication of flow sensors, showing good results, however adding more complex and costly fabrication steps. The sensing principle with a strain gauge is inspired by nature, where the drag force induced by the flow deforms the cantilever, causing an electrical impulse at the base. Such behavior can also be found in sensors of, for example, fish on the right. The sensor design is depicted on the bottom. It consists of a thick white top section on which the flow exerts the drag force, and a small thin section with embedded strain gauges acting as a flexure for bending. The drag force on the sensor scales quadratically with the flow velocity, whereas the relation between resistance change and strain is expected to be linear. Therefore, we expect a quadratic relation between the resistance change and the flow velocity. The design, as shown on the right, consists of three main sections: the drag plate, the flexure, and a section for clamping with the electrical connections. The strain gauges are 3D printed in such a way that they consist of paths directly running between the contacts, to prevent additional contact resistance between the printed lines. The sensors have a strain gauge on both sides to use differential sensing for improved linearity. The differential voltage is therefore measured with a Wheatstone half-bridge configuration. The sensors are printed with a multi-material FDM printer, the Diabase H series, with rotary tool head, as shown on the right. The orange material is a thermopolyurethane or TPU for the flexible parts, and the black material is a doped TPU, which is doped with carbon black particles to make it conductive for the strain gauges. One thing to note is that the resistance of the strain gauges is different on the top versus the bottom side, since the first printed layer has different properties than the succeeding layers. The differential sensing solves this issue. Several characterization steps are performed to do both a mechanical, dynamical, and aerodynamical characterization of the sensor. For the mechanics, a linear actuator is used to move the sensor tip and to measure the differential voltage, as done by Schouten et al., shown on the top right. The dynamic properties of the sensor are measured by exciting the sensor with a mechanical shaker, sweeping from 1 to 200 Hz. Finally, the response to a steady flow velocity is measured in an Aerolab wind tunnel from 0 to 10 meters per second in steps of 1 meter per second. As a first step towards an application in MAVs, the sensor is demonstrated in a feedback loop with a drone propeller to control a constant flow velocity. The differential voltage is measured with a microcontroller connected to Simulink real-time, which then controls the motor controller of the propeller. The setup is also simulated in Simulink to describe the sensor, where it describes the sensor as a second-order system with a resonance frequency and Q factor from the dynamic measurement and the sensor response from the wind tunnel measurement. Furthermore, a short delay between the propeller and the sensor is included for the time it takes from the air to travel from the propeller to the sensor, and the sampling is included from the microcontroller in the simulations. The results from the mechanical test with the linear actuator show nonlinear behavior for the differential signal as function of tip displacement, with both an upward shift of the signal over time due to creep, as well as hysteresis on the right figure. However, as an approximation for later use, a linear fit can be made. The measurement shown here is performed for 45 cycles, and you can clearly see that the loop shifts a bit upwards at the start of the measurement. The results from the dynamic test is shown on the bottom. From this data, a resonance frequency of 21.3 Hz is determined from the first peak in the frequency spectrum, and a Q factor of 4.4 is determined from the peak width at half maximum. This data can then be used to describe the sensor as a second-order system. The wind tunnel measurement for constant flow in the top graph indeed show the expected relation between the flow velocity and the sensor signal, as indicated by the square root shape-like fit in the top graph. The bottom graph shows what happens when first increasing and then decreasing the flow velocity does for the signal. Clearly, hysteresis can be observed in the measurement, which is likely due to the viscoelastic properties of the materials of which the sensor is made. Furthermore, for large flow velocities, we observed oscillations from the sensor. The sensor started oscillating. This could very well be explained by fluid structure interaction, where the flexible sensor starts oscillating because of the interaction with the turbulent aerodynamic wake behind it. The quadratic relation gives a changing sensitivity as a function of flow velocity. To compare this sensor to sensors from literature, we took a linearized sensitivity at 10 meters per second. The top graph indicates a 3% resistance change for the sensor between 0 meters per second to 10 meters per second. This is, for example, 1.5 times higher than for the doubly clamped, fully 3D printed airflow sensors from Aurobaya, but 15 times lower than for the molded PDMS sensors from Komat, which were both shown at the introduction of this presentation. The experimental and simulation results from the control demonstration are presented on the top left and right, respectively. The straight black line presents the set point, the blue the sensor signal, the red the motor signal, and yellow the control signal. The average flow velocity quickly arrives at the set point, but then oscillates around it due to the combination of the delay from the setup and the underdamping of the sensor, where the simulations on the top right show the same behavior. To solve the oscillations, the sensor signal is first filtered with a low-pass filter with a cutoff at 0.5 Hz to take out the sensor dynamics, giving a more stable but slower result for both the experiment and the simulation graphs at the bottom left and right. In conclusion, for the first time, a soft cantilever flow sensor has been 3D printed and characterized. The sensor is mechanically tested, showing hysteresis and creep, as well as a large Q factor of 4.4. Wind tunnel experiments demonstrate its functionality and approximately show an expected proportionality between resistance and squared flow velocity. In a control demonstration, the underdamping of the sensor in combination with a delay in the system causes oscillations around the set point. This was solved by filtering out the sensor dynamics from the sensor signal. All in all, 3D printing of soft cantilever flow sensors therefore shows potential for flow sensing. In future research, the sensor will be designed with a lower Q factor to improve the flow control. The fluid structure interaction will also be considered in the redesign. Furthermore, we will investigate benefits of linearization for the hysteresis, which can, for example, be done with compensation with power law models, as shown by Cosmas et al. And finally, the improved sensor will be tested in an MAV application. We would like to thank our funder. This research received funding from the European Union Council under the European Union's Horizon 2020 Research and Innovation Program. Thank you very much for your attention. Are there any questions?